In this video, we're going to talk a little bit more about polar reactions because there's so much cool stuff to note in here. So I'm going to start with ethylene. Now, of course, it's just drawn this way, ethylene. But because we're new to organic chemistry still, let's go ahead and draw the carbons in here just so we can remind you that they're there. And of course, you got to have 4 bonds to carbon, so there must be hydrogens there. This is what ethylene looks like. And if you remember, double bonds force a planar structure, right? So we're going to have these hydrogens and carbons all in a two-dimensional space here. And these carbons have pi orbitals. We're double bonded, right? So there's pi orbitals here, and there's pi bonding taking place here and here. That's what the double bond is. If you remember, sigma bonds, we talked about this in previous videos, but let's just make sure that we've got it fresh in our mind. If I put a carbon next to a carbon like this, and we have a shared electron bond, sigma cloud, right here in the middle, this is where 2 electrons are floating between the carbons, and then pi bonds form kind of like a hamburger bun over the top and bottom like this. Because ethylene is in this two-dimensional structure, maybe I draw it this way for this angle, you have this pi cloud just above it here like this, and it's rife for the attack. Look at all the angles I could come in and hit this electron cloud with some kind of an acid, or who knows what I want to bond it with. But the relevance here is that pi bonds, a double bond, a second bond, and a triple bond, same idea, are much more accessible than sigma bonds. Look in here. How are you going to get to that single bond? How are you going to get to the sigma space before you get down and penetrate into a double bond here? So they're going to get stripped first. Double bonds are very easy to strip compared to single bonds typically. So what might react with a molecule like this? We know that if we create an alkane, just carbon chain like this, carbon, 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 that of course between carbon and carbon the electronegativity is the same, so there's no dipole moment. It's relatively inert. But in an alkene like this hydrogen is going to provide a dipole moment to the carbons here like this, and this one here is going to provide it in this direction. So what you have here is a relatively negative orbital space. So this cloud in the sheet, let's draw that two-dimensional sheet here, looks like this. You might see a cloud that's kind of in the positive, see if I can draw that perspective a bit like that, and then negative, and then positive and positive. So when you have this double p overlap from these pi orbitals here, they are already relatively negative compared to what carbon would like to be. So they're already a little bit negative. They're already forming this wide open pi space up here. So they're going to be a little bit prone to attack by some kind of a positive space. I'm trying to keep my terms general here, but I hope you get what I'm saying. Now let's take this and see what we can do with it. So I love this two-dimensional kind of look because it gives us a better idea, and we know where the negative general space is kind of hovering above and below. So I'll draw like a dotted line because you can't really see the minus down there. But you get what I'm saying. You know where the cloud is right here. And I'm going to float in some hydrogen bromide. Hydrogen bromide comes floating by. Now bromine, that's a sturdy gal. Bromine is big. Hydrogen is about this big compared to bromine. There's definitely a mismatch in terms of atomic radius, but what really matters here is that hydrogen is not very strongly bonded to bromine because it's so far from the nucleus there. And I just want to remind you of that. Bromine is a big gal. There's a whole lot of rosy with bromine. So hydrogen can pop off of that thing, no problem. Hydrogen bromide is a strong acid as a consequence. This thing will just drop hydrogens all over you. And in this case, what's going to happen here is that this hydrogen is going to find that it actually likes this cloud space here, this negative space here is very attractive to the hydrogen that's being neglected by the large barrier, the distance it keeps from the nucleus and the electron cloud that bromine has to offer for bonding. So hydrogen is a little bit on the positive, right? So our dipole looks like this. And when you come across this negative space here, well, if you look at the free Gibbs energy, which we'll talk about later, this will react. This will react thanks to our strong acid here. So here's how the mechanism works. This double bond attacks this hydrogen here. So I want to, maybe we'll draw it sideways. Let's move this stuff out of the way and see if we can draw sideways here. I want to really want to show this. Okay, I've moved my molecule over. Let's bring the hydrogen bromide over. Now, this double bond attacks this hydrogen. And remember, this double-headed arrow means both that whole electron pair attack, not just one electron. This pi bond, it's floating above in that hamburger bun style, that open space there, attacks this hydrogen. And the hydrogen, his electrons are going to drop off over to the bromine. Bromine only needs a Br minus completes that energy level. So bromine minus is a pretty common thing to come across, right? But when our hydrogen attacks, think about what that creates. So we're going to end up with hydrogen, hydrogen, carbon, single bond now. The pi bond has been popped. And then we have a methyl group here, right? And of course, they provide all positive dipoles to that carbon there. So we want to keep that in mind, and that means that this becomes a little bit more electronegative than it was before. This guy's still electronegative in that way, but what's really interesting now is that because we have a Br minus hanging out this wise, now we have this carbocation because carbon doesn't like to be positively charged. It can be harassed into doing so, but look, we have this huge dipole this way over here, this carbon being much more negative spaced, right? This bromine is going to look over at this guy and say, you are short a bond. You're going to need my electrons over here, and I suppose I could share as long as you're willing to share back. So bromine is going to end up bonding here. And what we end up with is same side. Once you notice the hydrogen that was attached to this bromine here, same side, I'll draw it like this, just to kind of emphasize it here. We'll single bond everything up real fast like this. We end up with everything sigma bonded now. We've done what's called an addition reaction, where two separate molecules combine to form a single product. This is bromoethane, by the way. Bromo, because that is the halogen. They get priority in naming. And ethane, two carbons, and ane, single bonded. There you go, bromoethane. This is an example of an addition reaction. Should we do one more? Well, let's do one more example. I'm going to make propene instead of ethylene. Remember, prop means 3. Right? So we'll put that carbon there. Prop means 3 carbons. So let's see, 2 hydrogens fit on this, and this guy has room for 1 hydrogen. So here's propene. Clearly asymmetrical, right? I want you to remember that these are going to be sp2 hybridized because they're bonded to only 3 things, right? So these sp2 hybrids have their orbitals like this, but their pi bonds in 2D space here have this big open cloud space. We just talked about that. So they're definitely ripe for the attack. And what I'm going to do is I'm going to add water to this and sulfuric acid. Now when I put sulfuric acid in water, it protonates the water and water becomes H3O plus. So this is what I'm going to kind of look at here. Let's see what we can do. So here's my H3O plus. Now notice this oxygen is where the +1 formal charge is. And oxygen, as we know, being extremely electronegative, does not like that. It's going to be pulling very hard on the electrons in these bonds. Hydrogen is feeling the strain. Well, when you come along to this big open pi cloud here from this double bond, this is going to attack a hydrogen like so. And it's going to sever one of these bonds. Let's say it's this one, since this is where the most negative space is. Maybe we'll just think of this as the most positive space on the other side. But it really doesn't matter which hydrogen we talk about, right? Because this molecule is free to rotate however it likes. Now when we attack this right here, the proton will add to the less substituted carbon. Which one's the least substituted carbon? The least substituted carbon is the one with the most hydrogens. So this carbon in the middle here, it's more substituted than this carbon here. So we're going to see this hydrogen make its way to our end here, over here. We're going to form basically a methyl group with it, aren't we? Let's take a look at that. So let's take this away. We'll take this hydrogen off of here, and we're going to take this double bond away, and we'll add this hydrogen like this. Okay, and we're left with water over on this side because it left the electrons behind, and now water is reformed. Now again, remember, this is an addition reaction, so what we're going to do next is realize that this OH group is going to want to attack this very positive carbocation. Remember, we just created a cation here. There's only 3 bonds to this carbon. It's unhappy. So oxygen is going to use one of these electron pairs to attack that carbocation. And what we're going to end up with here is an OH group like this, attaching on like so. And what are we left with? Well, now that this water is gone, it spouts off this H+, which was what was sitting on that hydronium. So in the end, after this entire reaction is complete, this acid, this extra hydrogen that originally came from the sulfuric acid, is absolutely unused. So the amount of hydrogen ions or protons floating around in this solution hasn't changed. That's why it's called an acid catalyzed addition reaction. We've taken water and we've taken our propene and we've combined them into this propanol, or whatever we would say, because the alcohol group is on the second carbon here. So we've taken a double bonded carbon set and we've made it all single bonds, sigmas, right? But in the end, the amount of acid in the tank stays the same. We didn't consume that extra hydrogen at all. That's very important to pay attention to. Remember, addition reactions always take 2 things and combine them into one thing. So if you're looking at a test or something like that, keep that in mind. Addition reactions don't leave some partial product behind. They can leave a catalyst behind. We put an acid into this water through sulfuric acid to make hydronium, and that hydronium attached separate parts of the water to this molecule here, but ultimately it left its own proton in the solution that was used to form this product. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.